this video I'll be taking some more previous year questions from the chapter Fluid Kinematics. Okay, so this question, let's read it out first. For a two-dimensional flow, the velocity field is given as this, where I cap and j cap are the basis vectors in the xy Cartesian coordinate system. Identify the correct statements from below. The flow is incompressible, the flow is unsteady. You have to find y component of acceleration and x component of acceleration. Okay, for these first two statements, let's write the generalized continuity equation. Okay, I think I have derived this result in previous videos also, but okay, let's do it again. Generalized continuity equation, okay, which is del rho by del t. You know the notations: rho is density, u, v and w, which I'll be writing, are the velocity components in x, y and z directions respectively. Okay, so del by del x u plus del by del y of rho v plus del by del z rho w is equal to 0. This is the generalized continuity equation, okay, which can be written in the form rho del dot v vector is equal to 0. Okay, so now if the flow is steady, don't you think that this should be 0? So from 1, this equation 1, it becomes del by del y rho v plus del by del z rho w. Okay, u, v, w you know. So this is 0. Now if flow is steady, the equation becomes this. And also if it is incompressible, can I take this rho out from this partial differentiation? Can I take this rho out? Yes, I can. And after taking this rho out of this partial differentiation, what we get this equation, del u by del x plus, or let me write it here only, del u by del x plus del v by del y plus del w by del z is equal to 0. Okay, now this is a two-dimensional velocity vector is given, so we will be using del u by del x plus del v by del y is equal to 0. So this is the condition to check whether the flow is steady and incompressible. Okay, so now this is the u component of velocity and this is the v component of velocity. Let's see now del u by del x. Let's find del u by del x. Del u by del x is x square plus y square whole square. This differentiation you can solve, I guess. So this will be y square minus x square upon x square plus y square whole square. Similarly, find del v by del y. That will be equal to x square minus y square. Partial differentiation you can solve, I guess. X square by plus y square whole square. Okay, if you add both of them, you will get 0. So del u by del x plus del v by del y is equal to 0 is satisfied. That means the flow is incompressible and steady. Okay, so the flow is incompressible, correct. The flow is unsteady, this is wrong. Okay, now let's move on to the option number 3 and 4. This is a lengthy question, but it is a simple question. It's not a difficult question, it is just on your basics. Let me remove this part. Okay, okay, so what is, how do you write the x component of acceleration? Is written as u del u by del x plus v del u by del y and del u by del t. This is 0. Okay, so del u by del x you have found out. Okay, del u by del y, if you find out del u by del y, you can find out the component of x component of acceleration. So del u by del y, let's find out del u by del y. Del u by del y will be, I directly writing the result for you. You can differentiate, partial differentiate. This is 0 minus x 2y. This will be equal to minus 2xy upon x square plus y square whole square. Okay, you have u, you have del u by del x, you have, yeah, you have del u by del x, you have v, you have del u by del y also. Put all these values here. Okay, let me solve component of x component of acceleration for you, and you can find out y component of acceleration similarly. Okay, so ax will be x upon x square plus y square, this is u, into del u by del x. Del u by del x is y square minus x square upon x square plus y square whole square. Okay, plus y upon x square plus y square, this is v, and del u by del y is minus 2xy upon x square plus y square whole square. Okay, so that implies ax will be xy square minus x cube minus 2xy square upon x square plus y square raised to the power 3. This will be equal to minus x cube minus xy square upon x square plus y square raised to the power 3. Take out this minus x common, you will get minus x square plus y square upon x square plus y square raised to the power 3. This gets cancelled out. So x component of acceleration comes out to be minus x upon x square plus y square ka whole square. Okay, this is the x component of acceleration. Whereas in option 4, x component of acceleration is minus something x plus y upon x square plus y square whole square, which is not matching our answer. So that means this is wrong, and from the options you can see that third option has to be correct. Okay, so B will be the answer. However, you can find the y component of acceleration in a similar fashion. What will be the y component of acceleration? The equation that you can use, I will write here. Okay, ay is equal to u del v by del x plus v del v by del y. Okay, this will be the equation for the y component of acceleration. Okay, you know u, you know v, and you have found out del v by del y, so all you have to do is find del v by del x and put all the values here. You'll get the y component of acceleration. Be careful, it's a very lengthy question, and be careful that you have to put correct values. Like do not put del v del u by del x instead of del v by del x. Okay, you got the point. You have to put the values correctly. Okay, so the question was a bit lengthy, but it was on your basics. Next question. Consider the two-dimensional velocity field v vector, something u I cap, let it be u I cap. This is u I cap plus vj cap. Okay, where a1, b1, a2 and b2 are constants. Which one of the following conditions needs to be satisfied for the flow to be incompressible? In the previous question I have proved the condition. So apply del u by del x plus del v by del y is equal to 0. That implies del u by del x. This is u is 5 plus a1x plus b1y. Del u by del x will be a1 and del v by del y, what is v? V is 4 plus, this is, I guess, this has to be a2, yeah, 4 plus a2x plus b2y. Okay, so del v by del y will be b2 and this will be equal to 0. Check the options. A1 plus b2 is equal to 0, that is option B. So again on this concept there is a question. So you can say that you can directly remember the condition for the flow to be steady and incompressible. Okay, next question. For a steady flow, the velocity field is again given as u I cap plus v j cap. The magnitude of the acceleration of particle at 1 comma minus 1 is. Okay, so firstly I will find the x component of acceleration, then I will find the y component of acceleration, and then I will take the resultant. Okay, so x component of acceleration will be u del u by del x plus v del u by del y, and y component of acceleration will be u del v by del x plus v del v by del y. Okay, now find del u by del x. Yeah, so del u by del x, u is minus x square plus 3y, v is 2xy. Be careful while finding this del u by del x or del u by del y, all these partial differentiation. Okay, please be careful, you can commit error. So del u by del x will be minus 2x and del u by del y, del u by del y will be equal to 3. Okay, so del u by del x is minus 2x, del u by del y is 3. Del v by del x, del v by del x will be equal to 2y, whereas del v by del y will be equal to 2x. Okay, find x component of acceleration, that is ax, by putting all the values. Minus x square plus 3y into minus 2x plus 2xy into 3. Okay, and similarly ay will be minus x square plus 3y into 2y plus 2xy into 2x. Okay, I guess now you can put this condition that you have to find acceleration at 1 comma minus 1. You get x component of acceleration as 2 meter per second square, whereas y component of acceleration as 2 units. This will be 2 units because no units have been given, so this will be 2 units. This will be equal to 4. Okay, take the resultant. It will be equal to ax square plus ay square, a net, which comes out to be equal to root 20, and that is equal to root 5. The option is yeah, C. Okay, so in all the 3 questions we have used one condition is the condition for steady and incompressible flow, this condition, and the other is the equations for acceleration. So these topics are actually important from the gate point of view. You know, we have solved 3 questions, and in all those 3 questions these 2 concepts have been asked. Next question. Okay, most of the students, what will they do? They will leave this question without even studying, because there is drag coefficient and other equation, and they will not even read this question. So I will recommend you to at least read the question once. Okay, because these type of questions are mostly easy, in which the language is tough. I mean, when you start reading this question, you will see, yeah, that these type of questions are quite easy to solve. So let's read the question first. For the laminar flow of water over a sphere, the drag coefficient Cf is defined as, some equation is given, where F is the drag force, underline this, rho is the fluid density, okay, not the sphere density, U is the fluid velocity, D is the diameter of the sphere. The density of water is 100 kilogram per meter cube. This must be 1000 kilogram per meter cube. When the diameter of the sphere is 100 mm and the fluid velocity is 2 meter per second, the drag coefficient is 0.5. This is given. Okay, pretty simple to understand. If water now flows over another sphere of diameter 200 mm under dynamically similar conditions. Okay, great. Now we got the keyword, dynamically similar conditions. I guess in 2015 also there was a question on the same concept, dynamically similar condition. The drag force on this sphere is okay. So this, on this concept, the question has already been asked in 2015. Now for dynamic similarity, I have told dynamic similarity, the Reynolds number for both the cases will be same. Reynolds number for the case 1 will be equal to Reynolds number for case 2. I have solved this type of question in the previous video. That will be Vd by nu for case 1 will be equal to Vd by nu for case 2. Okay, nu 1 is equal to nu 2. Kinematic viscosity is for case 1 is equal to case 2 because the flowing fluid is water in both the cases. So that implies V1 d1 is equal to V2 d2. Okay, so V1, what is V1? V1, that is when the water is flowing over the sphere of 100 diameter. It is given as 2 meter per second. Diameter is 100 mm. V2 we have to find out in the second case. Okay, when the water flows over the sphere of diameter 200 mm. Diameter will be 200. That implies V2 will be equal to 1 meter per second. Okay, now we get velocity of the water flowing over the sphere of diameter 200 mm is 1 meter per second. Now what we have to find? We have to find drag force on the sphere of diameter 200 mm. What is the formula given? The formula is given as F Cf rho u square d square. Okay, put all the values. Cf is 0.5, rho is 1000, V we have found out. Okay, that is 1 square into d square, 0.2 square. This is in mm. Here you have to put it in meters. Okay, that will be equal to 20 Newton. So on this same concept, the question has been repeated. Okay, so the answer will be 20 Newton. Check the units in which you have to fill the answer, that is Newton. So 20 Newton will be the answer. Okay, so don't leave the question without reading it once. Okay, because the question which may seem difficult can actually be quite easy and can fetch you extra 2 marks. Okay, let's move on to the next question. The arrangement shown in the figure measures the velocity. Arrangement, this pipe should not be up to here, it should be up to here only. Okay, this is a correction, this pipe should be up to here only. Okay, so the arrangement is shown. The velocity of a gas of density, note the data, density is 1 kilogram per meter cube flowing through a pipe. Acceleration due to gravity is 9.81 meter per second square. If the manometric fluid is water, this manometric fluid is water, density is given as 1000 kilogram per meter cube, and the velocity of the gas is 20 meter per second, the differential held between the two arms of the manometer is. You directly remember the formula, you can use the formula and get the answer. However, I will derive the formula. Okay, I will not directly apply the formula, I will apply the concept. Okay, so this is a pitot tube. Okay, let me draw the figure first clearly. It's a rough diagram, but you'll be able to understand. In the GATE actual paper, you will see this kind of figure which I have drawn. Okay, we let here the point be A, and just here at the mouth of this pipe the point be B. Okay, this is the manometric fluid. Okay, can you tell me what will be the pressure at point B here? Because here the fluid is actually brought to rest isentropically. You remember the concept of pitot tube? Okay, so here V will be 0 because the fluid has been brought to rest isentropically. Okay, so at B the pressure will be PA plus half rho V square. The dynamic head will also be converted into pressure head, the concept of pitot tube. Okay, so PA plus half rho V square. Let's move on to this portion. The pressure here will be same by hydrostatic law. Let's move downwards. This is H, let this be Y, this height be Y. Okay, so we are going downwards, positive sign, rho gas G, total height will be H plus Y. Okay, now we come here, this is the water gas interface. We can jump from here to here because the fluid is same. Okay, so now we start moving upwards with the manometric fluid density, that is rho water G H, with the minus sign because we are moving upwards. Okay, these are the basic concepts. Okay, so this sign convention again we move upward, but here the fluid is that gas. Okay, so minus rho G Y is equal to, we reach point A, pressure is PA. We have assumed the pressure here at is PA. Okay, so solve this. This PA gets cancelled out, half rho V square plus rho G GH plus rho G GY minus rho water GH minus rho G GY is equal to 0. This gets cancelled out. Okay, so now we have to find H. That implies half rho G V square is equal to rho water GH minus rho of gas GH. Rho of gas is 1 kilogram per meter cube, V is 20 meter per second, rho of water is 1000 kilogram per meter cube, and G is 9.81 meter per second square. This is given, everything is given. All you have to do is put the values and get H. That implies H you will get as 0.0204 meter. But be careful that you have to fill the answer in mm. So that will be equal to 20.4 millimeter. Okay, this will be the answer. Next question. This was a nice question actually. The concept of pitot tube and manometry was used. So a 60 mm diameter water jet strikes a plate containing a hole of 40 mm diameter as shown in the figure. Part of the jet passes through the hole horizontally and the remaining is deflected vertically. Density of water is 1000 kg per meter cube. If the velocities are as indicated in the figure, the magnitude of horizontal force required to hold the plate is great. This water, when it will strike the plate, it will exert some force here. Okay, so we have to apply a force from here. Let that be Fx to keep the plate stationary. Can I say that the force required to keep the plate stationary, horizontal, is equal to rate of change of momentum in x direction. Okay, most of the questions from fluid machinery are asked on this concept only. Okay, so rate of change of momentum in x direction, this will be equal to m dot 1 v1 minus m dot 2 v2. Okay, and this can be written as rho a1 v1 square minus rho a2 v2 square. Great. And now fluid is water, we take rho common. A1 is pi by 4 d square. What is d square? 6 centimeter, that is 0.06 meter square into v1 is 20 minus a2. What is a2? Pi by 4 d square, 4 centimeter, so that is 0.04 square. v2 is again 20. Solve this, you will get fx is equal to 628.57 Newton. Okay, before filling the answer, check in which units you have to fill the answer. So that will be 628.57 Newton. Most of the questions from the fluid machinery are asked from this concept. It's a pretty important concept. This concept you have studied even in your 12th class when you must be studying for JEE mains or JEE advanced. Next question. A plate of width L is equal to 1 meter is pushed down with a velocity 0.01 meter per second towards a wall resting in the drainage of the fluid between the plate and the wall as shown in the figure. Okay, assume two-dimensional incompressible flow. This is given, two-dimensional incompressible flow, and the plate remains parallel to the wall. The average velocity draining out of the instant shown. You have to find u average. Okay, this u has been given as 0.01 meter per second. Okay, so this plate is moving down and the mass is exiting from these two directions. So can I apply mass conservation? Yes, I can. So by conservation of mass, so you see all the questions from the subject fluid mechanics are only based on your basic concepts, conservation of mass. Then you will encounter some questions from Bernoulli's equation in the coming videos. So I'll suggest you that you should clear your concepts crystal clear. I mean, so let's apply conservation of mass. Conservation of mass, that is m dot 1 is equal to m dot 2. Okay, so that will be rho 1 q1 is equal to rho 2 q2. So rho 1 is equal to rho 2. Okay, so q1 is equal to q2. a1 v1 is equal to a2 v2. Okay, now what will be a1? A1, let's assume that the length of the plate perpendicular to this screen is L. Okay, so this is perpendicular to the screen, I mean inside the screen. Okay, see it like this. So u1 a1, can I say that it will be equal to L1? Oh, this is L1, this is L. Okay, so let's assume it W. Okay, so L into W into v1. v1 is u, and a2 will be this length d and this width w. So this will be a2. Okay, but it is exiting from two sides, so you have to take into account the fluid exiting from this direction and the fluid exiting from this direction also. So the total q2 will be equal to u average into d into w plus u average into d into w again. Okay, so this is area 1, this is area 2. Actually these both are area 2, this portion and this portion. Okay, let me draw it more clearly. Something like this. So I have assumed this length that is perpendicular to the screen as W. This is L given, okay, this is D given, okay. So area A1 will be L into W, whereas A2 will be actually 2 into D into W. D into W. This area plus this area. Okay, because the fluid is exiting from both the directions. So this W gets cancelled out, and what is given? D is given as 0.1 meter. This is meter, and this length is given as 1 meter. U is given as 0.01 meter per second. So put this put all these values and you will get U average is equal to 0.05 meter per second. Okay, next question. A sprinkler shown in the figure rotates about its hinge point in a horizontal plane due to water flow discharged through its two exit nozzles. Okay, so it rotates about a hinge in a horizontal plane. Okay, the total flow rate Q through the sprinkler is 1 liter per second. The total flow rate, this is the keyword, do not forget this, it is the total flow rate, and the cross-sectional area of each exit nozzle is 1 centimeter square. Great. Now assuming equal flow rate through both the arms, so Q by 2 is flowing through this arm and Q by 2 is flowing through this arm. They have already given this also, so that you don't commit the careless mistake. Okay, so assuming equal flow rate through both the arms and a frictionless hinge, keyword, the steady state angular speed of rotation of the sprinkler is. Okay, so let us find the velocity. Firstly, let us find the velocity by which the fluid will exit from this this arm. Okay, so that will be equal to V is equal to Q by 2 into area is given as 1 centimeter square, so that will be 10 raised to power minus 3 by 2 into 10 raised to power minus 4. That will be in meter per second, so V comes out to be 5 meter per second. Okay, now let this velocity be V1 and this velocity be V2, the actual velocities by which the water will come out, taking into the consideration the angular velocity of sprinkler. Okay, if the sprinkler was not rotating, this would have been the velocity by which the water will be exiting, but as the sprinkler is now rotating in this clockwise direction, V1 and V2 are the relative velocities of water with respect to sprinkler. Okay, so this is the concept. Now this is rotating in the clockwise direction, so here there will be an extra velocity component in this direction which will be equal to omega r1, and in the arm of with the radius 20 centimeter, the velocity of component will be in downward direction, which will be equal to omega r2. Okay, so now the relative velocities v1 and v2, how can you relate v1 and v2? Can I say, as this is a frictionless hinge, net torque about the hinge is 0. This was the concept, and as the net torque about this hinge is 0, we can conserve the angular momentum. Conservation of angular momentum. Basics, your basics are have been applied in this question, that if the net torque about hinge is 0, you can conserve the angular momentum. Okay, so angular momentum is m dot v r1 is equal to m2 v r2. Okay, यार रुक यार, ये दोबारा करना पड़ेगा. Cut it. 25th question दोबारा करना है, दोबारा start करना है. 25th question. Okay. A sprinkler shown in the figure rotates about its hinge point in a horizontal plane due to water flow discharged through its two exit nozzles. Okay, in a horizontal plane. The total flow rate Q, keyword is total. The total flow rate Q through the sprinkler is 1 liter per second, and the cross sectional area of each exit nozzle is 1 centimeter square. Okay, assume equal flow rate through both arms. Equal flow rate through both the arms have been given, and it has also been mentioned in the figure so that you don't commit a careless mistake. So assuming equal flow rate through both arms and a frictionless hinge, keyword frictionless hinge, the steady state angular speed of rotation of the sprinkler is okay. Let's find out the velocity of exiting fluid without taking into the consideration of the angular velocity of sprinkler. Okay, so this can be found out by AV is equal to Q. Okay, but here, and I mean, let this be one first arm and this be second arm. Okay, so the flow rate is equal in both the arms, that is Q by 2. Okay, so velocity will be Q, total flow rate is 1 liter per second, that is 10 to the power minus 3 meter cube per second upon 2 into area. Area is 1 centimeter square, that is 10 to the power minus 4 meter square. So velocity will be in meter per second, and that will be equal to 5 meter per second. Okay, so this is the velocity when we have not taken the angular rotation of sprinkler into consideration. Okay, now the sprinkler is rotating in the clockwise direction. So due to this omega, there will be a component of velocity, that is omega r. For arm 1 will be the component of velocity due to this omega for arm 1 will be in upward direction and will be equal to omega r, whereas for arm 2 it will be in downward direction, and that will be omega r2. Okay, let me repeat it. So now when we take the angular speed of rotation of sprinkler into consideration, there will be an additional component of velocity which will be equal to omega r1 for arm 1, and that will be in the upward direction. Okay, and for arm 2, the component of velocity due to this omega will be omega r2, and that will be in the downward direction. Okay, because this is rotating like this, so for this arm this will be here in downward direction, this will be omega r, and for this arm the omega r will be in upward direction. However, this is r1 and this is r2, because these arm lengths are not same. Okay, so now what will be the relative velocity of the fluid exiting from arm 1? It will be V plus omega r1. Great. And what will be the relative velocity of fluid exiting from arm 2? That will be equal to V minus omega r2. Okay, now can you relate these velocities from any equation? Yes, you can. I told you this is the keyword, because net torque is equal to 0 on this system. Okay, net torque about this hinge on this system will be 0. So if there is no net torque acting on the system, can we conserve angular momentum? It was a nice question actually. Conserve angular momentum. This concept you must have studied in your 12th. You know, so see that the paper setters of GATE always ask questions from the basics. So if net torque is 0, you can conserve angular momentum. Now that will be equal to m1 v1 r1 is equal to m2 dot v2 r2. Okay, so the flow rate through both the arms is same. I'll be cancelling this out. v1 r1 is equal to v2 r2. v1 is the relative velocity of water from arm 1, and v2 is the relative velocity of water gushing out from arm 2. Okay, this is very important. So V1 is V plus omega R1 into R1 is equal to V2 is V minus omega R2 into R2. Okay, solve this, you will get omega as 10 radian per second. Take care of the units. Okay, take care of the units because V is in meter per second, so you have to put R1 in meters only. Okay, R1 will be 0.1 meter whereas R2 will be 0.2 meters. Okay, so what we have done in this question, firstly we have found out the velocity of water without taking into the consideration that the sprinkler is rotating, that is 5 meter per second. Now when we take the angular speed of rotation of sprinkler, there will be additional component of this velocity for both the arms. For arm 1 it will be acting in upward direction, for arm 2 it will be acting in downward direction, and from that we find out the relative velocities v1 and v2. Okay, after that we have just conserved the angular momentum. So this was a nice question. Next question. In a Lagrangian system, the position of fluid particle in flow is described as, some equation is given by x is equal to x naught e raised to power minus kt and y is equal to y naught e raised to power kt. Okay, this is the position of a fluid particle. Okay, in Lagrangian system the position is given as this, where t is the time while x naught, y naught and k are constants. The flow is, okay, we can say the flow is two-dimensional safely. Why? Because the position of fluid is described only in two coordinates. So this is sure that the flow is two-dimensional. Okay, we can write this safely. Now for steady or unsteady, what we can do is, we know the condition, but firstly we have to find the velocity components in x and y direction, because this is the position of the fluid particle given, not the velocity components of in x and y direction. Okay, so can I say dx by dt will be u, that is the velocity component in the x direction. Okay, dx by dt is equal to u and dx by dt will be x naught e raised to power minus kt into minus k. Similarly, dy by dt will give you the velocity component in y direction, that will be equal to v, which is y naught e raised to power kt into k. Okay, so now u is equal to minus k x naught e raised to power minus kt and v becomes k y naught e raised to power kt. Okay, x naught into e raised to power minus kt, this is x, see from the question, and this becomes y. So u is equals to minus kx and v is equals to ky. Now we know the condition for steady and incompressible flow. I've already proved this in the first question. It is del u by del x plus del v by del y should be equal to 0. Del u by del x is minus k plus del v by del y is k, this becomes equal to 0. So that means the flow is steady and two-dimensional. This is a good question. Many of the students committed error. They saw that here t is written, here t is written, so the flow is unsteady, but they did not pay attention to this word, that it was the position of a fluid particle given. Okay, so the flow is steady and two-dimensional. Thank you.